Hello friends and welcome at my channel. Today we're discussing a cosine rule, which is also important for many applications in trigonometry and for dot product, which is also important for vector product, which is also important for all kinds of applications in linear algebra as well, and so on. So we will see how it works, and I just show the proof of the theorem and of the rule, and maybe we'll just figure out that this is also nice to understand as a reverse Pythagoras theorem. So a lot of promises. Let's give it a go. So the statement is, if you have an arbitrary triangle, once again, so in every triangle, it holds that a squared is equal to b squared plus c squared minus 2bc times the cosine of the angle in between. B squared is a squared plus c squared minus 2ac cosine of beta in this case, and c squared is a squared plus b squared minus 2ab times the cosine of phi. Okay, so especially the last one, it's a kind of Pythagoras theorem, if you remember. This is a squared plus b squared equals to c squared. But you see, this part is kind of not available. So that means if we prove a cosine rule, we prove just a kind of generalization of the Pythagoras theorem, because the Pythagoras theorem, if you remember, was only applicable in right-angled triangle. So if the triangle is right-angled, we got this information, then we know a squared plus b squared equals to c squared. But the cosine rule is helping us to understand that if a squared plus b squared is equal to c squared, then this part must be 0. Well, if 2ab times the cosine of phi is equal to 0, well, these are positive values. Side lengths must be positive, otherwise we have no triangle. The only value that can be 0 in this case is the factor cosine of phi is equal to 0. But if you consider the graph of the cosine function, you'll see quickly that this value is 90 degrees. So that means phi is equal to 90. Well, we also have 270, but the sum of the angles is not further, and it cannot be more in our plane geometry than 180. I'll link it as well in my video. All right, the proof that I gave previously, 8 years ago or something, 9 years already. It's crazy. All right, so how can we prove this one? Well, let's prove just one of the equations, not all of them, because it's just a rearrange of the sides and nothing else, so no trick behind it. But you see, so if we know that a squared plus b squared is equal to c squared, then we also know that this disappears. But if that disappears, we know that the angle is 90 degrees, so that means it's kind of a reciprocal of the Pythagoras theorem. So once again, Pythagoras theorem is telling us, is it right-angled? Then a squared b squared equals c squared. But now we know if a squared b equals to c squared, then we know that the triangle must be right-angled, right? And that would, for example, help us, without showing anything or proving anything, to know that, well, if we have side lengths of 12, 5, and 13, we know for sure it's a right-angled triangle. We don't have to check it anymore. We don't have to draw it, nothing. Why? Well, because 12 squared plus 5 squared, it is 144, plus 25, it's 169, which is perfectly 13 squared. So a squared plus b squared equals to c squared is fulfilled in this case, and that means we know that the angle must be 90 degrees. So it's pretty powerful. All right, but let's prove it now. So this is an arbitrary triangle. I'm not asking for any kind of properties here. Non-isosceles, no equilateral, whatever we're having here doesn't matter. We're just working with an arbitrary triangle. And we're putting, let's say, so this is phi, and we are having this one 90 degrees, which is H, and we're having maybe P and Q again right here. And so let's see how it works. We are having also alpha, the opposite of A. Okay, so we have two triangles. This is the first one, right angled, and this is the second one, right angled as well. So this is, since the first one is right angled, we have P squared plus H squared equals to B squared. And in the second one, we have Q squared plus H squared equals to A squared. So that means in this situation that in the first equation we can solve it for H squared, which is just B squared minus P squared, and we can substitute it in here. So we're having A squared equals to H squared, which is B squared minus P squared, plus still Q squared. That's fine. So we have B squared, and now I'm just adding 0. So I'm adding C squared and subtracting it at the same time, so I'm not changing anything. Minus P squared plus Q squared. Now we see that C was constructed this way. It's the sum of P and Q. So I keep the first C squared value. The second one I'm rewriting as P plus Q squared minus P squared plus Q squared. So we're having B squared plus C squared. Now we use the binomial formulas. It's P squared minus 2PQ minus Q squared minus P squared plus Q squared. And now, well, make sure also we have minus, so we changed everywhere the signs. So minus P squared, I'm not canceling, but we can add them, but those two are canceling. So basically we have B squared plus C squared minus 2P squared minus 2PQ. So it is B squared plus C squared minus 2P, we're taking out, it's P plus Q. P plus Q is equal to C, so we have minus 2PC. And now if you look at this triangle, you'll see that if you have P and you divide it by B, that would be the cosine of alpha, so that means P is equal to B times the cosine of alpha. I can substitute P through B times cosine alpha, so it's B squared plus C squared minus 2 BC cosine of alpha. And if you check it, it's exactly the statement of the cosine rule. So once again, that's the proof, and also very important application of the cosine rule, not only being able to compute with two angles and with two side lengths and the angle in between all the other values in the triangle, I can also use it as a reverse statement of the Pythagoras theorem. Okay, thanks for watching, guys. See you in the next video and have a good day. Bye-bye.